What if it rained food? What if Earth was a cube? What if we had 9 lives? What if bits could fly? It's absurd. If money grew on trees, if we didn't have knees, if we walked through life slightly magnetical, it's absurd. Absurd Hypotheticals.
Hello everybody and welcome to Absurd Hypotheticals, the show where we overthink dumb questions so you don't have to. I'm your host Marcus Lehner, and I'm joined here today by Chris Yee and Ben Storms. Say hi, guys.
Hey, I'm Chris.
Hey, I'm Ben.
Guys, I am hyped for today because we get to go back up to the space and planet size scale with our Earth grab bag, which I'm pretty sure only materialized because I keep putting Earth-related questions onto our candidates list, and you guys won't do so many space episodes with me anymore.
I mean, a lot of those types of questions, like, it's hard to come up with 3 answers.
Yeah, that's mostly why we do these grab bags, but all at the same time, I did put a lot on there. But I'm happy we're doing this one. I'm sad I couldn't answer all of them myself, but I guess you guys must have a turn as well.
Actually, yeah, I think all 3 of these questions are your questions on the candidates list.
Oh yeah, absolutely. I think it's safe to say I am always the most excited about the space questions, but I will have to restrain myself because Chris, you are going first. So what is my space question that you answered?
Well, my question isn't really a space question. It's an Earth question, but it's what if Earth's elevation's doubled? So when I was doing this, I kind of ignored anything below sea level. So all the oceans, all the same, but then everything above sea level, like all the mountains are twice the height, all the cities are twice the elevation that they're at, stuff like that. So that's kind of how I handled this question.
Okay, so you didn't double the negative numbers.
No, I didn't double the negative numbers because I don't think do we consider those elevations? I guess.
Yeah.
We do.
Yeah, I'd say
technically.
so.
Yeah, it's the elevation of the seafloor is, negative a lot.
We usually say like a depth of instead of an elevation of, but I guess still technically it's an elevation. But yeah, I ignored the ocean.
Yeah, there's probably not too much interesting going on if you take the very deep bit and make it double deep. It's just still very deep.
I feel like we did that at some point too. We already did. Didn't we already do that? I don't remember when we would have done that.
Could have.
I don't think we ever specifically did that.
Whatever. Anyway, so the first thing that I wanted to do was to see what the highest elevation on Earth was because I wanted to see if we'd have like a real life space mountain sort of thing because that idea is cool to me. So first I found like the boundary of what we consider space, and there isn't really like an official boundary for outer space. I think we actually covered this before. I forget what episode, but there are different definitions. There's no official one. But the one that I used was that the U.S. classifies anyone that travels 50 miles up is an astronaut. So I use that as space.
Challenge accepted.
Now, Mount Everest is 29,000 feet in elevation. If we double that, that's 58,000 feet, which is 11 miles, which is not anywhere close to space. It's in the stratosphere. It's not space, though. So it's not, I mean, I was hoping for Space Mountain. It's not going to happen, though, unfortunately.
That'd be so cool. Like, that would definitely change up the Mount Washington bumper stickers, where it's like not, this car clown might watch, and it's like, this car is a spaceship, and I'm an astronaut.
So that's just like a little side tangent in the beginning. But so next I wanted to look at like where we would be able to live, and if there are cities that are like high in elevation, they're doubled, will they be in places that we can't live anymore because there's not enough oxygen? So I wanted to find like the highest place that we can live. And the highest permanent settlement in the world right now is in Peru. It's a city called La Rinconada. I don't know if probably.
I think it's pronounced Canada.
Yes, Canada and Peru. And the city is 16,700 feet in elevation. So I'm going to use that as our limit for where we can live as like a permanent settlement. Now, I found a histogram showing like the percentages of elevations on Earth, and it said that 28% of the land area is above 3,280 feet, and then 10% is above 6,560 feet. Now, there are like a whole ton of cities in Colorado that fit that 10% category. I think the average that I got was like 6,800. And if we double those cities, the elevation of those cities, they're really like they're coming pretty close to the limit of what we can live in. So a lot of those Colorado cities we won't be able to live in anymore. But that's just the US. So I wanted to look at more like worldwide. So I found a list of cities by elevation. In this list only included cities that had 100,000 people or more. But on this list I found 66 cities were in this 10% category of elevation, which means that if the elevation doubled, all 66 of these cities we would not be able to live in anymore. And the total population in these 66 cities added up to 46 million people, which is 6% of the world population.
Get down from there, population. What are you doing up there?
I know. They like to live with less oxygen, I guess. So if the elevation's doubled, pretty much, I guess the 6% of the population would have to go somewhere else and live somewhere else. So that's kind of like the result of just where we would be able to live and where we wouldn't be able to live. But another effect another byproduct of double elevations is that the land leading up to those elevations is also affected. So like the slopes leading up to tops of mountains are steeper now. So basically like every slope is going to be twice as steep. So I wanted to look at like what is the steepest street in the world. So the Guinness World Record has the steepest street in the world is Baldwin Street in Dunedin, New Zealand, and it is 35% grade, which translates to 19 degrees. So that's like officially the steepest street in the world, but there is an unofficial survey of Bradford Street in San Francisco. There's a 30-foot section that's the unofficial survey found that it was 40% grade, which is steeper. So that's unofficial, but it's in San Francisco, and that got me kind of looking into San Francisco because San Francisco is known as being like a very hilly city. It has a lot of steep streets that go up and down. So ignoring the unofficial survey, I want to see like what officially is steep in San Francisco. The steepest street in San Francisco, it's a tie between two different streets. So Filbert Street between Leavenworth and Hyde, and then 22nd Street between Church and Vicksburg. They both have a slope of 31.5%, which is around 17.5 degrees. So if elevation's double, then that means that both of these streets would be 63% slope. And then like all the other streets would be double slope too. So 63% slope is a pretty big slope. So the lower limit of a Black Diamond ski slope is 40%. Or 23% above that.
Oh, that kind of puts it in perspective.
Yeah. But San Francisco actually has like a train system in place to like climb the steep slopes. Not necessarily the double slope, but to climb the normal 31.5% slope. So they have a cable car system, and the cable cars are pretty efficient at climbing slopes. And the way that they work is that there's a cable beneath the street it's continuously moving. And that cable is powered by an electric motor that's located at a central powerhouse. And then the cars, when the cable car wants to move, it grips that cable. And then when it doesn't want to move, it lets go of the cable. And that's how the system works. And this particular cable system is good for slopes because it doesn't rely on like the friction between the road and the rail, or the car and the rail and stuff. It's dependent on the cable. So I couldn't find like an upper limit for how big of a slope this cable car system could handle. It can handle, obviously, in San Francisco, their slopes right now, but can it handle the double slope? So I found another cable-driven car system. It's called a funicular.
Funicular, yeah.
I've never heard of funicular before, but it sounds like Ben has.
They use them. I know they're more common in like obviously in like mountainous areas, but they're basically it's effectively a train. It's like a similar use to a ski lift, but not lifted.
Yeah.
Right. Yeah.
Right. Yeah. So as Ben said, it's used in like mountainous areas, and there's a reason. Well, I mean, so the way it works is that there are two cars that are attached to the same cable, and there's a pulley in the middle. and those two cars counterbalance each other. So as one goes up, the other goes down, and then vice versa. So yeah, this system is particularly good at very steep slopes. And the steepest funicular that I found was the Linton and Lynmouth Cliff Railway. It's located in North Devon in southwest England, and it climbs a slope of 58%, which is very close to our 63% that we need for our double slopes in San Francisco. It's only 5% off, and that 5%, if you translate it to degrees, is only 3 degrees. So I feel like it can handle the extra 5%. So we have cable car systems that can handle double slopes in San Francisco. But what about cars? Because maybe we don't want to rely on cable cars all the time. So for cars, I looked at Lombard Street in San Francisco. It's known, I guess people call it the most crooked street in the world. That's kind of what it's known for. It's like that windy street. You might have heard of it. You've probably seen it before.
Mm-hmm.
It's the one that just zigzags up, and you see it on all the movies and shows.
Whenever they show
stuff.
San Francisco, they usually show Lombard Street. So originally, Lombard Street was a 27% slope, but they kind of realized that was kind of too steep for cars, or it was just steeper than they wanted. So in 1922, Carl Henry, who's the property owner at the time, he proposed a design for a street that had 8 hairpin turns. So a hairpin turn is basically just like the street goes one way and then it turns almost 180 degrees or almost 180 degrees and just goes the other way. That's a hairpin turn. It makes a shape close to a hairpin, which is why it's called that. And using these 8 hairpin turns, they're able to reduce the slope from 27% to 16%. So it's an effective way to reduce the slope. They actually use this on a larger scale in like mountainous areas. They use on like hiking trails and stuff. So it's a good way to reduce the slope. So I figure if the elevation's doubled everywhere and San Francisco is twice as steep like everywhere, we're probably going to have these hairpin turns everywhere, and it's going to take a very long time to get everywhere because everything is going to be, all the streets are going to be longer. Not necessarily ideal because it takes forever to get anywhere.
We could get really good at drifting.
Yeah, we could have a San Francisco drift situation. But I thought it was not ideal. I came up with a genius plan. It's better than hairpin turns. Totally not ridiculous. Giant escalators for cars. Ben, what do you do?
So, I answer the question of what if the Earth's core disappeared? So, I guess just sort of to start, what is, at a base, what is the Earth's core? What is it? What does it do for us? So the core it's basically a partially solid, partially liquid, super dense, effectively chunk of an iron-nickel blend at the center of the Earth. And it's kind of the way it formed. This actually was a question I had as I started looking into this. I was trying to figure out if we would have like a new core form. Probably not, because the way the core formed is basically as the planet was forming, all of those dense, heavier metals just sort of sunk into the bottom and concentrated there. So got this big old ball of iron and nickel, this sort of orb of still kind of liquidy iron nickel around it. And all this iron nickel makes up a pretty good chunk of the Earth. It's actually about a third of the Earth's mass and almost actually half of the Earth's radius. So on some basic stuff, when this disappears, because it is about a third of the Earth's mass, gravity is going to change. Specifically, it's going to reduce by about that same amount. There's sadly not a planet that has that level of gravity, so I don't have a fun comparison, but it's probably not going to be enough that you get any real, fun impact from that, but it would be less gravity. That's kind of cool. Not going to matter. We'll get there in a little bit. Beyond that, first way this actually goes very badly is that probably the biggest thing that the core does is generate the Earth's magnetic field. It's caused by the rotation of the core. I'm not going to go too in depth into it because we actually had a whole episode about what if the magnetic field went away. That's episode 54 if you want to go find it. The short version is it's bad. The big important thing it does is it stops the atmosphere from being stripped away by solar winds. So that's not great. Once again, not really going to matter, but not good if the core has appeared. What's really going to happen to the planet is actually going to depend a lot on how this happens. And I figured we're going to go sort of in order of how complicated it's going to be to figure out. So let's start with the easy one first. Let's say that the Earth core disappears and it's replaced by a vacuum. This one's really simple. The Earth fills that vacuum explosively, or I guess implosively.
I guess implosively, and then probably explosively.
Yeah, so I think what winds up happening, the Earth isn't a perfect sphere. It's wider than it is tall. So I think what happens is, the mantle rushes in to fill where the core was. And kind of, as it all crunches in, it sort of bow out, further in the middle at the equator and sort of split and spread from there, which is cool. So that one's easy. That one's really easy. It's just the Earth implodes. So that one's pretty straightforward. What if, instead of being a vacuum, it's replaced by air instead? This is similar because once again we still have this big empty space in the middle of the planet. But instead of just explosively filling that void, the mantle is going to spread in at still pretty quickly because there's just this big old pocket in the middle of the Earth, but going to spread in more gradually. Fun fact, this is actually worse than if the planet just implodes. Because what's going to happen is that if there's air now in the middle of the Earth and the mantle is rushing in to fill it, that air has to go somewhere. And where the air is going to go is out, and it's going to go out through all the main means of like volcanic activity. So all that air is going to rush up through, gaps in the Earth's, like the tectonic plates and volcanoes and everything, and basically just cause like apocalyptic volcanic activity.
So slower death for us.
I actually maybe.
I love how apocalyptic volcanic activity is like the tame way to phrase what's happening.
Right, yeah, exactly. Yeah. We all die again, I guess is the big thing. But yes, I actually, it's funny you say slower. I don't actually know if it'll be slower for us.
I imagine an implosive, like the Earth imploding, would be pretty fast for us.
So, yes and no. So the core is like 30, it's like 3,700 kilometers thick. And it actually is a little over half of the radius of the Earth. So it's not going to be immediate. I still think that I think that it actually might be a little bit faster death with the volcanic activity because the air will start escaping immediately as the mantle starts spraying in, as opposed to having some delay on the implosion. Like, not a huge amount because giant vacuum, but it's going to be fast either way, I guess, is what I'm saying. It's not that much slower either way.
Yeah.
So that one's also pretty straightforward. So I was trying to figure out, because there are other things that I would like to talk about here, a way to make this work in a way that we could get to some different ways we die. So let's say that instead of having it immediately disappear, it disappears gradually. It kind of just like there's, a vacuum forming in the middle that kind of keeps getting filled in as the planet contracts to where everything that was core is now, I guess, mantle. What happens then? So once again, we're actually left with two possibilities. I'm going to start with the less fun one first. Fun is relative here. So let's say that the planet actually does survive this whole process, and we sort of crunch down bit by bit and just effectively replace our core with mantle. The planet actually isn't that much smaller. The core, because of the way that, like a sphere works, since it's the middle, it actually isn't a huge amount of the volume of the planet. It's only about 15% of the volume. And that means that the radius of the planet only decreases by about 370 kilometers of its current, 6,370 kilometers. So it's actually not that much smaller. There are a couple of problems. One, there's that whole, previously mentioned magnetic field issue. Maybe more immediately, I'm not sure exactly. And I don't have good numbers on this because I couldn't figure out a way to calculate it. None of our water is going away. So if somehow we survive the core going away and the planet contracting, which admittedly are pretty big ifs, we are going to deal with some pretty dramatically rising sea levels.
Oh, yeah. And we're really just kind of on a rounding error on having land at all anyway, so...
Right, exactly, yeah. So I think there's a couple of things that can happen here. It's either just obviously we all, get crumble into various bits as the planet contracts, or we all get flooded and it's basically a water planet because it's enough smaller, even though it's not actually that much smaller, that the water sort of overtakes everything.
What about those people in the 10% of high elevation? Do they drown?
So, unsurprisingly, there's not good, like, data on how much sea levels would rise if the core went away. Or I guess if, like, the planet shrank overall by a certain amount.
Potentially that 6% that die in my situation could survive in your situation.
It's possible. It is possible that a tiny amount live. There is one other problem, and this actually could take place in the more explosive possibilities as well. So obviously there's a lot less gravity on the planet. There's another impact of that aside from just, jumps are fun, which is that the planet is spinning very quickly, and the planet's not necessarily as solid as you might think about it being. And if the rotation of the planet doesn't slow down, what likely is going to happen as the core appears is, as the gravity reduces, bits of the Earth are just going to kind of slough off into space.
Ooh, good. That's fun.
So, once again, I couldn't get a good, good model of how this is going to happen because pretty far into a hypothetical here. It's entirely possible that in one of those ones where the core just disappears, that's actually what gets us, not the decompression. We just kind of get flung off in all directions, which is maybe more fun. I don't know. But I do think that at a certain point in the gradual loss one, that's also going to start happening. So I would imagine the first to go would be those ones with the high elevations, actually. So probably unlikely that they make it, even if they don't get drowned by the rising seas.
But they get the most fun way to die, in my opinion.
It is pretty cool, I'd imagine. Yeah. So I will say, researching this was a lot of fun because it's rare that I find so many exciting ways for us to die in one question. Usually it's one good one. Here I got 5 or 6. So that's fun. I really tried to figure out a way to get to a point where we had a working planet with no core. I don't think it's possible. The other thing I couldn't figure out, I don't know. This is one of those things where I think just lack of knowledge about how planets work is tricky. Not like on my particular case, but just as a, scientific research study. I don't know if you could have a planet that didn't have some sort of solid bit in the mantle is relatively liquid. I don't know if you could have a planet spinning that's relatively liquid, down to the core, and have it maintain any kind of structural integrity.
You know what you could have, Ben? You could have a donut-shaped planet.
I love the idea. I love the idea the planet just turns into a baker spinning dough on his hand.
Just the top and the bottom collapse into the middle and it all goes to the edges and you just have a big old donut planet. And we've done that one we've done before.
We did that one. This is not how we got there.
No.
So I guess long story short, unsurprisingly we die. Surprisingly we can die in any number of ways. I don't know what my favorite way is.
So you've killed us with magnetic field disappearing, which is a previous episode.
Yep.
The planet becoming a donut, which is a previous episode.
Yep.
Us being submerged in water and having to live underwater, which is a previous episode.
Also true. Have we ever been launched off into space?
We've lost gravity. We've
lost gravity.
Before.
Okay, so that technically is relatively the same. So a previous episode. Any other ones? I guess technically we did Flora's lava, and that's a pretty
yeah.
That's an outcome. So I gave you 5 prior episodes and 1 here. This is a very high value question.
Yeah, listen to this. Just listen to that Ben's one answer. You never have to listen to any other podcast episodes.
Well, no, please keep listening to the podcast. But you could, I guess, technically. Anyway, yeah, unsurprisingly, if the Earth's core disappeared, we would die. Just, pick your poison, I guess. Marcus, what did you do?
So the question I did was actually the endpoint of a couple of answers I've had in the past about planet formation. And my question is, what if Earth was a gas planet? So I'm going to start with saying that basically all the information I'm using here is based off of Jupiter. I understand Jupiter is much bigger than Earth and also has a slightly different composition, like it's got a lot of ammonia. But my first instinct was to try to see if I could make what Earth is made out of generally and make it into gases. The problem is, Ben, like you mentioned, it's a lot of iron and nickel, which just isn't in a gas form.
Right.
So if I take what Earth's made out of and make it into a planet, it's just a rocky planet, not a gas planet. So basically what most gas planets are made out of is pretty much just hydrogen and some helium, and then basically trace additional stuff based on, your specific flavor of planet. But what I use is Jupiter because we have the most data on what it's like inside Jupiter, mostly because we flew that Galileo probe just like into it and just collected data until it stopped.
That feels very rude on our part, honestly, if you think about it.
It is, especially because like he had a bunch of other missions. Like he went to check out like a bunch of moons, and like it was all this multi-part mission. And then the end of the mission was, okay, and now we're just going to dive you into Jupiter, and you're just going to send data until you die. But anyway, going on to what if Earth is a gas planet, the first and most obvious problem with trying to live on a gas planet is that there's no actual, surface to live on. So if you try to go onto it, you just kind of keep falling through the atmosphere until, physics eventually stops you. You won't get to reach the center of your planet because as you go deeper and deeper into a gas planet, the pressure continues to increase because the atmospheric pressure is basically the weight of all the stuff on top of you pushing down. So it squishes, and it gets denser and denser and denser as you go into the planet. And when you're talking about planet scale type stuff, eventually the pressure is going to compress all those gases enough that they'll be just as dense as you are. And then you'll end up kind of just floating somewhere at some level. So the question is kind of like, where is that and what does it look like when we stop? So as I just mentioned, we did use Jupiter. I did use Jupiter's reference point because that's where we sent the Galileo. So let's take a look at what happened to our good buddy robot. Basically, so from the top of Jupiter's atmosphere, it descended about 1,150 kilometers into the planet before data stopped being sent, is how they phrased it. So let's start by looking at the pressures, because the pressure is going to kind of inform the density of the gas. So the higher the pressure is, the denser the gas is, and the closer it will be to buoyant. So the pressure ranged from effectively 0 at the top of the atmosphere, because that's, the space barrier. It hit 1 bar, which is, the equivalent of the atmospheric pressure on the surface of the Earth. So 1 bar at about 1,000 kilometers out of its 1,150 down. And then that last 150 kilometers ended up being at 22 bars, or 22 times the Earth's surface pressure when the data stopped. So the bad news for getting this answer completed is that this is nowhere close to where we'd stop falling. As a point of reference for density, because again, we're trying to get the density to be the same between the gas and us so that we float. As a point of reference, hydrogen gas is compressed in scuba tanks so that can be stored more effectively. You can get more gas in there. Sorry, oxygen, not hydrogen. But anyway, just to get a reference on how much gas is compressed. So the pressure in a tank is about 700 bars, and that brings the density of the gas from 0.09 kilograms per meter cube to 42 kilograms per meter cube. So 500, close to 1,000 times as dense. The problem is the average human has a density of slightly less than water, it puts us at 985 kilograms per meter cube compared to our compressed gas of 42. So we're not even close to the density that we need under the pressure. And compounding that is that, we're nowhere the 700 bars of pressure density is nowhere close to what we need, and we're nowhere close to that 700 bars of pressure anyway for where the probe stopped reporting. And kind of compounding on that bad news is that as you go deeper and deeper into Jupiter, it gets hotter and hotter, and even where the probe stopped transmitting, it's already being about 300 degrees Fahrenheit, which is not the craziest number physics-wise. That's a manageable temperature. But if you're wondering, maybe we can just keep going deep and, in a ship that insulates for temperature and pressure, it's not really going to work out for us because, like I said, 300 degrees is manageable, but it is estimated that the core of Jupiter can reach 42,000 degrees Fahrenheit.
So I guess this answers my question of it's not going to be like a hot tub, huh?
No, it's not going to be like a hot tub.
Damn it.
Yeah, 42,000 degrees is just well and way above beyond the melting point of any substance. Like, you know, you can make a tungsten ship and it's just gonna melt.
I was gonna say 300 degrees is not space scale hot, but that the core of it is space scale hot.
Yeah, so I don't have data for when the where it shifts to like just absolutely unbearable temperatures, because we couldn't take temperature readings that deep because our Galileo exploded. But you can tell shit's going down because of some of the cool stuff that starts happening to the hydrogen gas. For example, at about another 1,000 kilometers down from where we are, the pressure is high enough to turn the hydrogen gas into liquid hydrogen. So just by squeezing hydrogen together, it has turned it into a liquid. And then if you go, you know, another section down in Jupiter from that, it goes from liquid hydrogen into liquid metallic hydrogen, where not only are they so close together they act like a liquid, they're so close together that the individual electrons on the hydrogen atoms dissociate with their own nuclei, and it becomes a sea of hydrogen like a sea of electrons around a bunch of nuclei, which does some cool stuff. And the reason they call it metallic hydrogen is that it now acts like a metal and it picks up some of those properties. So like this liquid metallic hydrogen is magnetic, conductive, and interesting enough, very reflective. It's like if you had a pool of it, it would be like mirror-like on how much light it reflected.
What if everything was a mirror? That's a previous episode.
All right, Chris, you're on episode watch here. So yeah, you can't try and go deep down. The heat is gonna basically ruin any plans you have of trying to make it workable. But the good news is that there are actually a couple areas where you could try and live temperature-wise. So interesting, the upper atmosphere of Jupiter, like right at that space barrier, gets incredibly hot. It's up to like 800,000 degrees Celsius up there. And this is basically because of the energy from the sun hitting the planet and getting trapped in those gases. So we actually have on Earth too some pretty hot spots at the top of our what do they call it? The ozone layer. That's the one. So kind of like where the sun's radiation isn't quite deflected yet, it'll heat up and then it kind of dips down. Jupiter's a bit different than Earth as far as the heating goes, because the majority of Jupiter's quote-unquote energy budget isn't actually from the sun. So Earth, if you look at like global warming and stuff, the temperature where we are is more influenced by the sun than the core of the Earth being, you know, hot molten magma and radiating outwards. It's almost entirely from the sun's energy. Jupiter's a bit different. So basically, once you get to the 1 atmosphere zone, kind of, the temperature of the sun really is kind of irrelevant, and it's partially because Jupiter has a bit of a thicker atmosphere, but also Jupiter's just that much further away from the sun, so it's getting less energy per, you know, square foot emanating from the sun. But Jupiter is much hotter on the inside and much better about getting that heat outwards. That said, there is a gap between the hot outside and the hot middle. The higher side of our good temperature range, I'm calling it, is about 700 kilometers down, where the pressure is roughly 10 to the minus 5 atmospheres. So this is one of the sections that Galileo was able to reach. Low pressures are generally okay for like equipment and vehicles and what we'd be using to otherwise survive in this gas planet, because there's really only ever a max of 1 bar of pressure difference between like the inside where you'd be and the outside. You know, it can't get any more extreme than just being in space. You can't go less pressure. The only bad news is that we're basically at 0 atmospheres. The humans can't survive in pressure that is less than like 0.35 atmospheres, because that's the point where our blood starts to boil, which is not good for you. I've heard.
I've heard, never experienced.
So that's the high side of that temperature gradient. The low side, where you start getting hot again, is actually right at the range between 1 and 5 atmospheres, which is great because 1 atmosphere is what we live at currently. Our bodies are much better at handling high pressures than low pressures. So there have been people who've spent hours in pressures as high as 70 atmospheres. So 1 to 5 is no big deal for us.
7? How long do they live in the 70 atmospheres?
I think it was like they were working in a specific I forget if it was a dive or if it was like in a pressurized container. But they were there for like 2 hours.
70 is a lot.
70 it is the record for for atmospheres. But I didn't look at the diving numbers, but I think divers are regularly like in the double digits of pressure, because water is a lot heavier than air, so the pressure picks up quite quickly once you go underwater. So there's a couple. So basically, if you can stay and maintain your altitude in this range, you can actually live in at least from a pressure and temperature standpoint, have a livable area. Staying afloat is kind of tricky, because like my first idea of like, oh, you just have a big balloon and it'll be fine, is that it's hydrogen air, so it's hydrogen gas, so the air surrounding you is already the lightest possible gas. You can't go less dense than hydrogen gas if you're just like filling a balloon with something. You can't make yourself more buoyant. The only way I say that, but you actually can a little bit. So what you'd have to do is you'd have to have like a hot air balloon. When you heat make a big balloon, heat the hydrogen gas in it so it's a higher temperature on the outside, and then you'd have a bit of a density differential where you could float. There's a decent amount of pressure, and so you can still actually also use just plane physics to stay at that level too. So all the mechanics of flight would work in this at this stage in the planet. So again, feasible, but there's like two last problems here that'll probably just kill us eventually. One of them is wind speeds. Basically, because it's all this hot gas and this liquid metallic hydrogen spinning around and all these crazy things going on with these gas planets, they're a lot more mobile. I'm going to say mobile than rocky planets. Jupiter spins more than twice the speed of Earth. And part of what that spin creates is wind, like high winds. So you see all the storms and the big red spot on Jupiter and all that. So they've logged wind speeds regularly of 384 miles an hour around Jupiter storms, so that's not uncommon. And that wind speed is even higher than the scale of an F5 tornado. So if you were trying to, fly a plane, if you had a Jupiter space plane, you might have some problems with the weather. And then the second one, which I think is going to be a bigger problem, is convection. So I mentioned how the upper atmosphere of Jupiter is hot because of the sun's rays, sun's energy, and all that. They're actually, when they did a study on it, they found areas on Jupiter's upper atmosphere that were even like hundreds of degrees hotter than they would have expected. And basically what's happening is the hot lower parts of Jupiter, it's all gas, so they can move in between each other. So there'll be air currents and drafts of this hot air coming up from deep in Jupiter and going up into the atmosphere. So even like specifically above like the big red spot, they were hitting temperatures of over 1,000 degrees Celsius, all above the red spot. Like basically from the red spot upwards, just it's boiling, because that's like a heat escape for the gas planet. So I don't know how variable they are, except for the fact that they are quite variable. So you could basically create a ship, you could have it be at that level, and things would be generally okay until either it got windy or suddenly all the temperature around you just went up by hundreds and hundreds of degrees and fried you alive. And so if Earth was a gas planet, it would be generally bad.
Less variety than Ben's.
Less variety than Ben's, but more facts about Jupiter.
Undisputable.
All right. With that, we have talked about the Earth and un-Earth-like planets enough. We'll move on to our Would You Rather question. Okay, Chris, are you ready?
I'm ready.
Would you rather have an indestructible car or home?
Huh.
So your car probably gets into situations where it would need the indestructibility more often, but it's more devastating if your home is destroyed. Also, I don't have a car.
Well, would you rather? Well, you also don't have a house, so would you rather have an indestructible home or an indestructible car?
I guess I don't. I mean, I live somewhere, so I have a home. I don't own it, but
see, I think you're thinking about this the wrong way, Chris. because you're looking at it in a purely reactive manner. You can't use an indestructible home for anything. You can certainly use an indestructible car for things.
True.
See, if you're only thinking about it in terms of like, what do I least want to have destroyed? The answer is clearly your home. However, you can, I mean, I feel like none of the things you can do with an indestructible car are particularly like...
I mean, what would you do with it, though?
I mean, that's what I was trying to figure out, but you could do things with it, and that's what really matters.
You can hit stuff with it, but like, what would you want to hit?
I mean, you could open like a demolition company where you just break buildings by driving your car into it repeatedly.
That'll be controlled.
I think the part of the problem is that cars aren't very good at hitting things, actually.
Here's a question: if your car is indestructible, does that mean you're not indestructible inside the car?
No.
No, you're not. That's actually a very, very compelling argument.
So it'd still be pretty dangerous if you're inside it, but...
You basically would just have an old car from, like, the 70s before, safety regulations were a thing.
Right.
But, I mean, you could hook up some sort of remote control situation.
True. Okay.
Yeah. I mean, you can do stuff with it. You could probably do something with an indestructible home as well as, like, a space for, like... I don't know, bomb testing? Like,
okay, that's not necessarily the direction I was going to go, but...
I mean, what's the point of having a bomb test on indestructible home? You don't... Like, what are you trying to test?
It's contained. See if it explodes.
Well,
like, you could close your front door. You could, like, close your doors and just drop a nuke inside, and then it would be fine.
I mean, that doesn't tell you any information, though. Like, usually a bomb test is like, what kind of destruction did it cause?
But you can still put, like, measuring equipment inside and see, get the data.
The data of what? Of
how
bomb?
Big your bomb explodes. You can get, like, pressure data, I'm sure.
I mean, it's going to be warped data because it's in an indestructible home, which doesn't exist in any other situation.
I think if you dropped a nuke in an indestructible home and everything was contained, you'd basically just make a sun.
There you go, infinite energy.
The energy can't go anywhere.
Unless one of the windows is cracked, in which case you've made like
a space laser.
Death blade.
Yeah.
If you have an indestructible home, does that mean that you can't do renovations?
Probably.
I mean, you can add on.
I want to do it like the best version of it, like where your house won't take any. Like, you can renovate your house, but won't take any damage you don't want it to. I would say your furniture and stuff inside is not safe, but anything that's like permanently installed, like your kitchen and kitchen appliances, I think are generally okay, but not like your couch.
All right. I think the key to all this is actually the fact that you are not indestructible in your car. And if that means that if you get in like a car accident, it's not the fact that your car breaks that's going to kill you, right? It's going to be the fact that you stop suddenly. So the indestructible car is actually pretty not helpful the more I think about it.
The indestructible car could be used as a submarine.
I don't think they're watertight. Cars aren't watertight, right?
I don't think cars are.
Not submarine watertight.
Yeah.
It's got like an air intake, which is an immediate problem.
I feel like a pretty important component of a submarine is the ability to come back up, which I don't think your car can do. I
mean, you could attach an engine to. You could attach like a jet engine to it. I don't know, not like a air jet, but like a water jet. I don't know. How do submarines go?
Why don't you just get a submarine then? Why would you use a car to do this?
Would you have an indestructible submarine or an indestructible car? Go.
Submarine. Done. Okay. Car or house? How about that one?
Yeah.
I mean, I'm leaning towards house just because it seems more practical.
Yeah, I'm finding difficulties finding the usefulness of the indestructible car, actually, the more I think about it. So unless you got a really big selling point right now, Marcus.
It goes back to my first point where, yeah, it doesn't save your life if you're in a life-threatening accident, but if you're in a smaller accident, it saves you money.
Plus, even if you were in a, even if it did save you, like if you took the great version of the car's indestructible and so are you inside it, you're still not going to be able to just drive recklessly. You could still kill other people.
Right.
Well, he wanted to use it as like a wrecking ball for demolition.
Yeah, or some other, I don't know. That was just the first idea that came to mind and probably the only one that's really feasible, but...
You know what? I was just thinking movies would be a good spot for it if you had like a stunt car for movies that you don't have to worry about crashing and exploding. But honestly, a stunt house for movies might be more practical than that.
Explain.
I don't agree with that.
I think I'm leaning towards Chris's answer on this one, yeah.
Like, if you need to shoot a bunch of scenes, like, how many buildings and how many sets and shit do you have to explode to get your explosion scene and all that going?
Yeah, but then your explosion scene, the house isn't going to get destroyed.
There's just going to be a fireball and the house is fine.
Yeah.
Not after CGI graphics.
Well, then just but wait.
Then just don't have a house at all. Just have
okay. Maybe I didn't think that one through. All right. Let's try and call this one. This one. I feel like we're not making much headway here.
So in terms of the movie thing, the car is useful. But in terms of practicality, I think the home is more useful.
Overall, I'm going to say home is better.
I think home is better too. I'm also a little biased because we just had I was visiting my folks' place and we had like a water pipe break in the basement. I'm like, damn, I don't want to have to deal with that shit.
Yeah, it saves you a lot of like small expenses, not small expenses, but expenses like that.
Yeah, it saves you a bunch of medium-large expenses that you just have to suck up and spend money on. And the car, you crash the car and you just get a new, you're going to spend less on cars than you will on house repairs, I think, in the long term.
Yeah, I mean, you still have maintenance for cars too, but it's generally less money for car maintenance than house maintenance.
Yeah.
So I'm going house. I think all of us are.
Yep. Houses all around.
Plus, I'd like to just have a house.
Also that.
Indestructible or no.
Yeah, it's worth more money.
All right, well, that'll do that. We all want the indestructible home. If you enjoyed this episode and would like to support the show directly with your hard-earned dollar that you saved by having an indestructible car and or home of your own, go to www.patreon.com/absurdhypotheticals. Click on that Become a Patron button. It is one tier at $1 a month. You're welcome to give more, but with one singular dollar, you unlock all the behind-the-scenes episode that we do every month, where we workshop new ideas for the show, where we talk about our previous month's episodes, where we chat about how we make the show. A lot of real good, behind-the-scenes stuff.
I think in the latest one, we're talking about a new segment or a new episode that we're doing for the end of the year.
Yes, we are changing our end of the year format, and we're going to just figure it out live on our next behind-the-scenes episode. So if you want to be in for that discussion and see why we do the things we do, you can go and check it out right there.
It's our previous, because it airs, so we recorded this before it, but it's airing after the BTS.
Yeah, I think it's the one that actually came out last Friday if you're listening to this on the day it comes out, right?
Yeah.
Guys, you're giving away all the behind-the-scenes stuff. They have to pay for it. But yes, the one the behind-the-scenes that just came out, we'll talk about the year-end show. And the one next time, we'll talk about God knows what. I'm excited.
I'll talk about 2021 because it'll be a new year.
Jeebus. Very excited to be out of this one. All right. Well, we're out of that. We're getting out of this year and now getting out of this episode right now. You can join us next week where, fitting for how much we talked about old episodes on our answers this week, we're going to be doing another throwback episode where we revisit questions of episodes past where we're like, we could do better on that one, huh? I'll see you then. Why do I say that? I never say that.